We're going to be looking at a special case of Newton's laws known as equilibrium. So to start, please answer the following question in your bell work packets. True or false? Stable architectural structures such as the Golden Gate Bridge and the St. Louis Arch have no forces acting on them. Explain your reasoning in 1 to 2 sentences. Okay, so you can pause the video here as need be, answer this question, and we'll move on to our next topic. Okay. So today we're looking at 3.2, equilibrium, okay? To give you a hint of what we're looking at, equilibrium means equal or balanced, like this rock right here is balanced on this perch, okay? So some announcements, the Monday we come back from the weekend, all right, we'll have a quiz on equilibrium, okay? In this case right here, it will be again open note, we'll spend the latter half of class going over the quiz. So what we're up to today, all right? Learning how to apply special cases in Newton's laws to scenarios that involve civil engineering, such as the construction of bridges and buildings. And then recognizing when a physical system is stable and what that entails, aka what's the significance for a physical system, to be stable. All right, so applications of equilibrium. Equilibrium is responsible for modern infrastructure. Okay, we'll take a look at what equilibrium means in a second. Equilibrium, again, is responsible for modern infrastructure. Okay, and it's very fascinating from the physicist's perspective because we analyze the forces acting on a system in order to help us design structures such as bridges and the St. Louis Arch and buildings that keep the bridges stable and safe from falling down. From the mathematician's perspective, equilibrium is interesting because we take those forces in order to determine an equation so that our system will be in equilibrium, meaning that our system is stable, okay? So like the St. Louis Arch, the shape of St. Louis Arch is actually what we call an inverted catenary curve, so it actually has a specific mathematical function that it takes the shape of. And same way with the Golden Gate Bridge, the spans of the Golden Gate Bridge are actually parabolas because it turns out parabolas are actually the most stable configuration for the Golden Gate Bridge. All right. We can see this from the design right here. They have these special functions that they use to design the shape of the Golden Gate, of the Golden Gate Bridge right here, a parabola for the cables, and then the inverted catenary curve for the St. Louis Arch. Catenary meaning that it forms a U shape, and then inverted meaning that's turned upside down. So what is equilibrium? Okay, so equilibrium refers to when the net force on an object is zero. Okay, meaning all the forces balance and equal each other out, hence why we have a state of equilibrium, okay? So there are two types of equilibrium. The first one is static equilibrium. So when the net force is zero on an object at rest, the object will stay at rest. This is known as static equilibrium. Static because static means to remain at rest, okay? So the conditions we have is that the net force must be equal to zero. And as a result, the acceleration is also going to be equal to zero. So static equilibrium is the most important goal that civil engineers aim for when they're designing buildings and structures like the St. Louis Arch and Golden Gate Bridge. Because if you have a net force acting on your system is going to begin to accelerate. And what that's going to have is disastrous consequences if it's, say, the Golden Gate Bridge. Yes, we can have it sway a little bit, but not too much. Otherwise, the Golden Gate Bridge, buildings, the St. Louis Arch will all collapse due to that net force acting on them. So the goal is always to aim for static equilibrium with civil engineering structures, okay? And then the key word to pay attention to is at rest, okay? So when we're dealing with equilibrium problems, the key word we want to pay attention to is at rest for static equilibrium, okay? Next, we move on to dynamic equilibrium. So if you recall Newton's first law states an object will either stay at rest or maintain a constant velocity unless a net force acts upon it. So static equilibrium refers to that first case where object stays at rest. The second case where object moves at constant velocity refers to dynamic equilibrium. So when the net force is zero on a moving object, that object will maintain a constant velocity. Like people on an escalator, the people on an escalator have a net force of zero acting on them, they move at a constant velocity. So that would be an example of dynamic equilibrium. Other examples of dynamic equilibrium would be, say, a hockey puck that's sliding on ice or a car that's moving at a constant velocity on the highway, meaning that the engine is counteracting the force due to friction, keeping the net force at zero, acting on the car. We call this dynamic equilibrium because dynamic means to move, okay? So again, the net force is zero and the net acceleration of our system is zero. But the keywords to watch out for here are constant speed or constant velocity. So static equilibrium the keyword was to look for at rest, And then dynamic equilibrium was to look for constant speed or constant velocity. So how do we check for equilibrium, okay? We're going to start with some simple examples here, and then we're going to build up to some more complicated examples. So the easiest way to check for equilibrium here is to add your forces together in the x and y direction separately, okay? The y direction acts in the vertical direction. All forces in the vertical direction are not going to affect the horizontal direction, vice versa. So we only add together forces in the horizontal direction, and we add those together separately from forces in the vertical direction. So for example, right here, our net force in the horizontal direction would be 0 newtons. 5 newtons to the left and 5 newtons to the right. So our object would be in equilibrium in the horizontal direction. However, in the vertical direction, we have 5 newtons of force acting downwards. So we're not going to be in equilibrium in the vertical direction. Likewise, right here, we're going to have equilibrium in the horizontal direction. We have 2 newtons acting to the left, 2 newtons acting to the right. But we're not going to be in equilibrium in the vertical direction because our net force is going to be minus 5 newtons plus 2 newtons, which is going to give us negative 3 newtons of force acting downward, okay? So we sum the x and y forces together separately, all right, to see if we're in equilibrium. All right, in this case, in case number 2, right here, we have 2 newtons of force acting up and 2 newtons force acting downwards. And then we have 5 newtons of force acting to the left and 5 newtons of force acting to the right. So in the vertical direction, our forces balance each other out. Minus 2 newtons, positive 2 newtons. And in the horizontal direction, our forces balance each other out. Minus 5 newtons, positive 5 newtons. So the overall net force in our box is 0 newtons. Okay? And then lastly, if we look at this last case, we have a case where we're not in equilibrium in any direction at all because we have a net force in the x direction, horizontal direction. We have 5 newtons of force to the right and 3 newtons of force to the left, which means overall we have 2 newtons of force to the right. And then we see in the vertical direction, we have 2 newtons of force acting upwards. So we're not in equilibrium in the vertical or horizontal direction. So the only case where we have an overall equilibrium is case number 2. So vectors in equilibrium. Recall that vectors are arrows that we use to represent different physical quantities like velocity, acceleration, and force. So equilibrium can be determined visually by performing vector addition, what we call the tip-to-tail method. If the vectors add together, aka the arrows added together form a closed loop, we say the object is in equilibrium. All right, meaning a zero sum. So the tip-to-tail method right here, what that means is we connect the tip of one vector, aka the tip of our arrow, to the tail, aka the end of the other vectors, okay, in order to get their sum. So for equilibrium, the vector sum of the forces is 0, meaning we get a closed loop, okay? So let's take a look at an example right here, okay? So let's say we have F1, F2, and F3 as our free body diagram, and we want to know if this system is in equilibrium with those 3 forces acting. So what we can do right here, okay, is we can take, let's say, is we can take F1, we can start F1 right here. So here's the tip of F1, and now we're going to take the tail of F2 and connect it to the tip of F1. And so F2 is now pointing as it was before, except now it's connected to the tail, or excuse me, tip of F1. And then where we have the tip of F2, we take the tail of F3 and connect it. So here's the tail of F3 connected to F2. And now we draw F3, again, in the same direction F3 has over here, and we see if our loop is closed or not. In this case, we can see we have a closed loop, okay? So we can see that this is a case of equilibrium, okay? Now, let's do a quick check for understanding, okay? So which of the diagrams, if any, represents an object in equilibrium? Okay, so you can pause the video and work on this if you'd like, or we can go through it together if you'd like to do that, okay? So which of the diagrams, if any, represents an object in equilibrium? So again, we're going to use a tip-to-tail method, so we start with this diagram right here, okay? So what we can do is we can take this top vector, we can start with this top vector, and then we can connect the tip of this top vector to the tail of this vector right here. So we have the tip of this top vector connected to the tail of this bottom right vector, and so this bottom right vector is now going to move down here. And so now we take the remaining vector and we connect the tail of the remaining vector to the tip of this vector right here. And when we do that, we can see that we get, when we do that and we draw the last vector, we can see we get a closed loop telling us we're in equilibrium. Okay? And then for number 2 right here, we can do the same thing with number 2 right here. Okay? So we start out with this vector right here. So here's our vector, we draw it, and now we take the tail, or excuse me, the tip of this vector and connect it to the tail of the vector that's pointing up and to the right. So now a vector that's pointing up and to the right, we draw that. And then we lastly draw this vector that's pointing just straight up, and we connect its tail to the tip of the vector that's pointing up and to the right. In this case right here, we can see that there is not an equilibrium case. We don't get a closed loop, so we're not in equilibrium, meaning there is a net force acting. Okay? So the important thing here is, again, the tip-to-tail method, okay? And you can actually add the vectors in any order you want, and you'll still get the same result. So you don't have to do it the order I showed here. You can do it in any order you want, so long as you adhere to the tip-to-tail method, okay? So let's take a look at problem solving with equilibrium, okay? So a 1,300 Newton man is standing on a platform that's acting as a temporary bridge that weighs 30,000 newtons. At the point where the man is currently standing, the tension in the left cable is 16,000 newtons. What must be in tension in the right cable in order to keep the bridge stable? So we follow the same procedure as we did with 3.1, where we first draw a free body diagram to label all forces acting. Then we sum our forces together by Newton's second law. aka we determine the net force, just like we did back in 3.1. Except the only caveat now is instead of solving for acceleration, we're now going to solve for an unknown force because our acceleration is 0 when we're in equilibrium, and hence the right-hand side of our equation, F equals ma, is going to be 0. The net force is 0, so we sum all our forces together, and then we set this equal to 0 to solve for our unknown quantity, which is a force that we're trying to determine. So let's take a look at what that looks like in a problem here. So first we're going to label all forces acting. So we're going to have the tension of the left cable. We're going to have the weight of the man, which is 1,300 newtons. Okay? We're going to have the weight of the bridge, which is 30,000 newtons. Okay? Again, weight is different from mass. We're given newtons right here, so we know that this refers to the weight, the gravitational force acting on a person, and not the mass of the person. Okay? Same thing with the bridge. And then lastly, we have the tension of the cable on the right, which is what we're trying to find. The problem asks us to find tension in the cable on the right. So here's our free body diagram for this specific scenario. So the next thing we're going to do is we're going to use this free body diagram in order to sum our forces, all our forces together. So we're going to have 16,000 newtons of force acting upwards. So 16,000 newtons, positive 16,000 newtons. We're going to have 1,300 newtons and 30,000 newtons acting downwards. So we're going to have minus 1,300 newtons, minus 30,000 newtons. And then we're going to have this unknown tension in the right cable that we're going to try and solve for. And it acts upwards, so it's going to be positive plus t to the right, okay? So this is our net force, this is our sum of forces, and again, because we're in equilibrium, we set this equal to 0, okay? So now what we do is we solve this resulting equation for the tension on the right, which when we do, tells us the tension on the right should be 15,300 newtons, slightly less than the tension in the left-hand cable. This makes sense because our person is located closer to the left-hand cable, so the left-hand cable is going to be more tense in order to support this person's weight than the tension in the right-hand cable, okay? So now let's do a problem together, another one together. So a window washer that weighs 800 newtons is sitting on a platform that consists of a pulley system of a rope that has a standard tension of 900 newtons. If the washer is to pull the platform up at a constant speed, what must be the force with which she pulls? So again, we draw our free body diagram. We have the weight of the person, okay? We have the force due to tension as a result of the person pulling, we have the force of the person pulling, and as a result of the person pulling, there's going to be tension in the rope going upwards. But then there's also going to be tension on this side right here. So that's how a pulley works, is the pulley is going to create multiple sources of tension. So there's going to be tension on this side from the person pulling down, and then there's going to be tension on the other side as a result of that tension supporting the person inside of the pulley, or inside of the washer, okay? The platform, whatever we want to call it. So in this case right here, we're going to have two sources of tension, all right, of 900 newtons each, okay? Please note that I have three sources of tension here, but this is because I used a slightly different problem last year. So your free body diagram should only have two sources of tension, okay? And then we have the force acting downwards, and then we have the 800 newtons of weight acting downwards as well. So this is our free body diagram. So now we proceed to the next step where we sum all our forces together. So we're going to have 2t now instead of 3t. Again, this is the modification I make. So we're going to have 2t minus 800 newtons, okay, minus F equals 0. Okay? So as a result, 2T is going to be 2 times 900 newtons minus 800 newtons minus F equals 0, or 1,000 newtons minus F equals 0. Again, it says 1900 right here, but the calculations I'm making is with 2T now. So you're going to have 2 times 1900, which is 1800 minus 800. So you're going to have 1,000 newtons minus F. And then we solve for unknown force, which is going to give us F equals 1,000 newtons. Okay? So the problem's slightly modified from how I did it last year, but the problem solving process is still the same. We draw the free body diagram. Again, we have two sources of tension. One that's counteracting the person pulling down, and the other that is supporting the weight of the platform. Okay? We sum our forces together, set equals 0 because we're in a case of equilibrium. We can see that with constant speed. And then we solve for our unknown, which is the unknown force. Okay? So we do have a prediction challenge right here that each of y'all can test out on your own if you would like, but it's not certainly required. Okay. If you would like to skip over this prediction challenge, you can, but if you would like to test it out on your own, there are materials at the front in order to do so. So a mass of 1 kilogram that is at rest on a surface is pulled upward for force of 6 newtons. Sketch a free body diagram for this scenario. Okay. So the free body diagram scenario, if you want to test yourself out, you can do that real quick, pause the video. If not, we'll move on from here. So our free body diagram is going to be 6 newtons of force acting upwards from pulling. We're going to have the normal force acting upwards as well. And then we're going to have the force due to gravity, or the weight of our mass pulling downwards. Okay? So in this case right here, what happened here? Here we go. So in this case right here, again, we proceed to sum all our forces together, okay? So we're going to have 6 newtons of force plus some normal force minus Fg, okay? And again, we set that equals 0 because we're at rest, telling us we're at equilibrium. So we're going to have 6 newtons plus the normal force minus 1 kilogram times 9.81 meters per second squared. Notice how we're given mass here instead of weight, so we need to find our weight by multiplying 1 kilogram by the acceleration due to gravity. So 1 kilogram times 9.81 will give us 9.81 newtons, or we can round that up to 10 newtons. Okay? So as a result, we're going to, when we take 6 newtons minus 10 newtons plus normal force, we're going to get minus 4 newtons plus normal force, or the normal force equals 4 newtons. Okay? So you can test this out yourself with a spring scale and a scale and a digital scale that I have in the back if you would like. Otherwise, you can proceed to work on classwork 3.2 for the remainder of class.